You don't need any oxygen for those fires. You have a strong oxidizer here in nitrate, and so even in the absence of oxygen, those would have been burning, just like the CO2 and magnesium, but in this case, the ammonium was burning. Does ammonium burn? Yes, it does. It's a great fuel. And if you think about all that power and those explosions comes from this, a -3 and a +5, you know, just that imbalance in electrons created that much energy. Well, we see this type of stuff in these mixtures here. So for example, when I see this as being a very dangerous reaction. Ethanol and potassium permanganate and HCl. This one is particularly important for Chem 1B because I had a student making up a lab. Did I tell you about this? The explosion? I had an explosion here in that hood over there. One of the students was making up a lab. They used ethanol in an experiment. But the following experiment, they were using powerful oxidizers in strongly acidic solution. And so I told the student before the lab, you know, don't mix the waste from your experiment with today's waste. You know, put it in a separate jug. Well, what they did was, I guess in the rush of the experiment, they poured the ethanol in the jug of powerful oxidizers, and then it exploded. It exploded up, so the mouth of the waste jug was open, fortunately, and the bottle, it was a glass bottle, it didn't shatter. So I got really lucky, but it just exploded up. But the only bad thing was the student was you know, the bottle was tall and the student was shorter and was trying to reach in to pour it, and so part of their head was stuck inside the hood when it went off. And so they just got burns on their face and the hair was burnt off. Got lucky at that time because if the bottle exploded and shattered, then there would have been shrapnel everywhere. It would have been bad news. But you know, when I see that, you know, when I think about ethanol pouring into a bottle of oxidizing acid, strong oxidizing acid, you know, I see disaster. I see what that reminds me of is, you know, there's a big fire and somebody going over there with a gallon of gasoline and then just pouring it on top of the fire. You know, it's just like that, or just well, anyway. And so hopefully these, as you see more and more of them, they'll make more sense. But a lot of these use a copy down. So ethanol we figured out. But permanganate, you know, we just copy that down from the chart. And so permanganate plus. One thing about the chart you'll notice is this. A lot of these need H+. For example, nitrate required H+, but under certain conditions, it really didn't. And so let's take a look at that chart again, briefly, and then see something about this. Here, permanganate plus H+, you know, look at it, ozone up to the top plus H+, hydrogen peroxide plus H+, permanganate plus H+, lead peroxide plus H+, plus H+, plus H+, plus H+. A lot of these require H+. And so when you look at this, do you see a pattern? Do you see something that all the ones that require H+ have in common? Is there a pattern to that? There is a pattern. They all have oxygen, yeah, that's one. There's another thing. Take a look at the product side. Do they all share something in common on the product side? They all form water. If you didn't have H+, you know, what you'd end up with is oxide. Is oxide very stable? No. And so we have that. Oxide can form, you know, stable compounds with other species. But that's one thing. And so we need H+ here. So you can kind of figure out how many H+s we need. You know, if I have one permanganate, how many H+s do you think I'll require? Well, I need to form some water, so I'm going to have 8 H+s. This you just copy down off the chart, plus 5 electrons. This is going to yield Mn2 plus 4 H2O liquid. So this one's a lot easier to figure out because you just copied right off the chart. This one was pretty tough. We had to figure that out. Now the next thing is we have the two half reactions. This ethanol is producing 12 moles of electrons, but the permanganate, each mole of permanganate only consumes 5 electrons, 5 moles of electrons. And so what we have to do is we have to balance the electrons. That is, the moles of electrons consumed must be equal to moles of electrons produced. The way we get these to balance is by changing the coefficients. And so let's do that. And so if I want these electrons to balance, how many should I have? Like 60, 5 times 12. So let's go with that. And so 5 times 12 will be 60, 12 times 5 will be 60. So we'll cross multiply. Here it's going to be 5, 20, 10, 5, 60, and 60. It gives us our 60 electrons produced. And then we need 60 electrons consumed. So we'll have to multiply this by 12. 12 times 8 is 96. It's going to give us 60 is 12. 12 times 4 is 48. And there are 60 electrons consumed. So the electrons have to balance and cancel. If they don't, then something's wrong. All right, then we add up the two half reactions. So let's go ahead and do that. Over here. We'll take 5 ethanols. Plus 20 H2Os. Plus 12 permanganates. Plus 96 H plus. Okay, this is going to produce 10 CO2s plus 5 waters plus 60 H plus 12 manganese 2s plus 48 waters. Did I screw something up? Yeah. I should have simplified this one more. Where did I get that other water? That's all right. We'll do it in the next step. So 48 H2Os. All right, now let's simplify this. So see, I got 53 waters here and 20 waters here. So let's get rid of the 20. Then this will end up giving us 33 waters here. Now I have 60 H pluses here and 96 here. So we'll get 36 left over there. All right. So that looks okay. So we're going to go 5 ethanols. Plus 12 permanganates plus 36 H plus is going to produce 10 CO2 plus 12 Mn2 plus 33 waters. All right, this should be our balanced non-ionic equation. Let's just make sure it's balanced. Let's check charge and atoms. So let's start off with atoms. We got 5 times 2 is 10 carbons 10 carbons. And this is 6. This 30 hydrogens plus 36 is 66 hydrogens. That's 66 hydrogens. And then 5 oxygens plus 48 is 53 oxygens. This would be 20 plus 33 is 53 oxygen. So the atoms are balanced. And then we check the charge. This is minus 12 plus 36 is plus 24. And over here it's plus 24. So plus 24 and plus 24. The charge is balanced. And so we have our balanced net ionic equation. That's what we get when we do the chart method. We just get the net ionic equation. We don't get the complete or the ionic. After this, we have to determine if there's a driving force present. And so we saw earlier that ethanol is going to be a reducing agent, and permanganate and acid, this is our oxidizing agent. Powerful oxidizer. But going in the reverse direction, what's our oxidizer and what's our reducer? And so in the reverse direction, well, the easiest place to see it is in the half reactions because of the conjugate relationship. If you go back to the half reactions, the reducer ethanol produces its conjugate oxidizer. What was the conjugate oxidizer? That is, ethanol goes to what? CO2. And so CO2 is the oxidizer. As in one direction, it loses electrons. In the opposite direction, it takes electrons. So CO2 takes electrons to go back to ethanol. The permanganate in acid is our oxidizer. What's its conjugate reducer? And so in one direction, it takes electrons. The other direction, it gives up electrons. And so the conjugate reducer would be manganese 2 plus in water. Reducer. All right, here you have to use some chemical knowledge, just basic factual knowledge in determining which one do you think is a stronger, more powerful oxidizer. Permanganate in acid or CO2? Do you need a chart for this? Because it isn't on the chart. No, you shouldn't need a chart for this, because which one do you think will be a stronger oxidizer? Permanganate in acid, by far. And so this is stronger, this is weaker, therefore we have a driving force. That must mean ethanol must be stronger than this. This one's tricky, because I don't know, ethanol versus manganese 2, which one do you think is easier to burn? Ethanol or manganese 2? Probably ethanol by a large margin. But anyway, we have driving force here. All right, any questions on this? This was a challenging problem, but you have to use some knowledge. Like, for example, ethanol being flammable, but what if I did something like glucose or sugar? If I put sugar here, glucose, is glucose or sugar flammable? Or sucrose, table sugar? Can you burn table sugar? When you burn table sugar and you completely burn it, what does it burn to? Carbon or carbon dioxide? Well, that's actually incomplete. You're talking when you caramelize sugar and you make that black. Yeah, that's incomplete oxidation. I'm talking about throw sugar in a fire, and what's going to happen? Are you going to get a nice caramelized? No, it's going to be completely burnt to CO2 in water. And the same thing happens in your body. If you consume ethanol, do you know what it eventually ends up as? CO2. You exhale it. When you eat sugar in your body's just undergoing these redox reactions. Do you know what's going to become of that sugar? You're going to exhale it as CO2. You know, because your body's not going to go partial. Your body's going to completely oxidize that stuff to get the maximum amount of energy. Can you get even more energy out of it? No. Once you get to CO2, that's it. It's done. Okay, let's take a look. Some more. We don't have to have complete oxidation or complete reaction. We could have partial reactions. When you have these partial reactions, then you know, it depends on the conditions. You know, are you going to get complete combustion or incomplete combustion? Well, it depends on the conditions. Well, these will give you more insight as to the conditions. You know, over here we see manganese in the +7. Over here we see manganese in the 0. Well, these are pretty much two extremes of manganese. You know, manganese really doesn't form negative charge species. Metals don't usually form anions. And so what we see is we see this, the range here. +7 is the most electron poor. 0 is the most electron rich. But wait a minute. In the last reaction, what we saw is that the permanganate went to manganese 2. It didn't go all the way to manganese. How come? And why didn't we go all the way to manganese in that last one? The reason we didn't go all the way to manganese is because that wasn't the choice. The only choice we had for permanganate was this. Permanganate goes to manganese 2. There are no other permanganate entries here. So what does that tell you? That tells you, based on observations, the most common redox half reaction for permanganate is to go to manganese 2+. Right? But we could go to other species too. So for example, if we went to MnO4 2- with manganese in +6, or MnO2 with manganese in +4, or Mn3+ with manganese in +3, these are all possibilities. And it depends on the conditions where we stop. So if we're doing more advanced reactions and we have, you know, these partial or incomplete oxidations or incomplete reductions, then we got to consult something like this. This is called a potential diagram. Potential diagram shows us how things can react. So and here you can see it as well. There are many oxidation states between 0 and +7 that we can stop at on the way. Oh, this is more advanced, so this is not part of Chem 1B. So you don't have to worry about this. Instead, what we're going to do is we're just going to assume that when we combust organics, they go all the way to CO2. Or whatever. If they're nitrogen containing, they'll form NOx and whatnot. All right, so the potential diagrams we aren't going to worry about, but skeleton redox we are going to worry about. But skeleton redox, this is chapter 5 material. And so chapter 5, let's take a look at some of the homework problems in chapter 5. Here are the steps in balancing skeleton redox. You know, we separated the skeleton half reactions. We balance all elements other than hydrogen and oxygen. Balance the oxygen by adding water. This is just what we did for ethanol. But it was only one half reaction. And so take a look at this reaction here. Do you recognize this? This is ethanol. This is ethanol in permanganate. We have a powerful reducer and a powerful oxidizer. This is a dangerous combination. Do you see that? But look at the products in this reaction. In this particular reaction, we have what we call partial oxidation. So the conditions must have been milder because we didn't have complete oxidation. If we had complete oxidation of ethanol, what should it form? CO2. If we had partial oxidation of ethanol, it could form other products. So when you drink ethanol, it doesn't immediately go to CO2. When you drink ethanol, if you drink ethanol, then it gets oxidized to acetic acid first, and then on and on and on. Actually, an aldehyde first, what they call it. Say. But something like this, we see it's being partially oxidized. In this case, it's forming acetate. And the manganese, the permanganate, the manganese isn't going all the way to Mn2 plus in this particular example. In this particular example, we're going from permanganate to MnO2, manganese 4 oxide. And so here's a case, under certain conditions, reaction conditions, we form different products than other conditions. Well, how do you predict it? These are hard to predict. So what you do is you just try the reaction under a whole bunch of conditions and see what the major products are. And so that's the whole point of skeleton redox. What they did was they mixed these two together, and these are what formed. Well, now what we want to do is we want to get the full balanced equation. To get the full balanced equation, we separate this into half reactions. So the first half reaction is ethanol goes to acetate. That's different because earlier we did ethanol goes to CO2, right? And then we balanced that out. This one is partial oxidation, so ethanol goes to acetate and then balance it the exact same way. And then permanganate goes to MnO2. In the previous one, we had permanganate goes to Mn2 plus. This one's different. I'll let you finish that one. And then we have these other ones, like here, HS minus and HSO3 minus goes to S2O3 2 minus. This is an example. If we reverse this, this is the example of disproportionation reaction. On the forward, it's kind of like a combination. These form the same. But this is a redox reaction. And so what we have here is when we split this up into the two half reactions, we have one, HS minus goes to S2O3 2 minus, and then the second half reaction would be HSO3 minus goes to the exact same product, S2O3 2 minus. So we have these both going to thiosulfate here as the product. And then balance it. All right, here we have this one, AS2S3 and NO3 minus going to this. Okay, so the arsenic ends up where? The arsenic ends up here in arsenic acid. The sulfur ends up here in elemental sulfur. And so AS2S3 goes to both of these. So it has two products. Whereas nitrate would just go to NO here. And so we separate those into two half reactions and then balance. Here we have CRI3. The chromium ends up in chromate. The iodine ends in periodate. And so CRI3 produces two products. But what about the H2O2? Where does the H2O2 go? And so CRI3 goes to this and this. H2O2 goes to nothing, but that's not a problem because H2O2 is a hydrogen-oxygen containing compound. Any hydrogen-oxygen containing species is automatically balanced in this procedure, because if we go H2O2 goes to blank, then we balance all elements other than oxygen and hydrogen. Well, there's nothing else. Then we balance the oxygens. So we have two oxygens here, zero oxygens here, which means we need two waters here. And so we just add two waters. And so in other words, hydrogen peroxide will go to water plus other stuff as we complete the balancing process. Is methane flammable? Yes, the methane is electron rich. How about ammonia? Does ammonia burn? Yes, ammonia burns. And so you could fuel the fire using methane, or you could fuel the fire using ammonia. But if you fuel the fire using ammonia, watch out, because you could form toxic substances, NOx. Oxides of nitrogen are toxic. That's what oxides of nitrogen dioxide is what gave the brown smoke in the Texas City explosion. But anyway, going back to this is a bad combination. If you have a methane flame, I do not recommend spraying ammonia in there. Because if you have a methane flame and you spray ammonia, what potential product might you generate? So methane, and you add a little bit of ammonia in there, and you might form hydrogen cyanide gas. Hydrogen cyanide gas is extremely toxic. How do I know that? How would I have predicted that? You know, it's one of those things where the conditions, you know, you change the conditions, you change the product, right? And so this is one of those things. They just do it by mix it and check. You know, they don't predict this theoretically. So under certain conditions, they form hydrogen cyanide gas. It's a dangerous reaction here. Hydrogen cyanide is very toxic. All right, but you don't want to get caught up in a lot of theory. You know, the initial part, and a lot of people get stuck because they start thinking too much. When you first learn these, you know, steps, just follow them. It's like when you first learn the ideal gas law, you just plug in the numbers, plug and chug, they call it. You know, just punch in the keys in your calculator. Do you have to really understand the theory, you know, of gases to use the ideal gas? No. And the same thing here. Do you really have to understand the properties of each of? No. All you have to do is you have to just be able to look up the value or look up the compound in the chart, copy it off there, and write it down on a piece of paper. So a lot of people get stuck because they're thinking too much. So for example, you know, I had one student who was asking me about the hydrogen peroxide and nitric acid problem on the homework. And they said, well, they Googled it, and they've been looking, they've been trying to research it, you know, what's supposed to form. But then I asked, you know, did you try doing the steps? You know, step 1, step 2, step 3? No. And the thing is, if they just did step 1, step 2, step 3, they'd get the right answer, you know, chances are, as long as they're following the steps. And they don't even have to think, you know, what are the properties of hydrogen peroxide? What are the properties of nitric acid? They just have to follow the steps, look at the chart. You know, that's what the way most of the homework is. You just do the steps and you should get the right answer. You don't really have to think much. And then later, after you do a bunch of these, then you want to start thinking, you know, why is this a powerful oxidizer? Or why is this an especially weak reducer? You know, those are questions that come up after you get the basic steps down. Anyway, are there any questions with this? No. Okay, we're going to take a break. Let's take a 15-minute break, and we'll start again at 3:40. Okay.